This talk is about protect errors. This might be mostly interesting for people who write C code and implement packages in C. I'm part of the rcore team, so I'm working with Martin and others, and what I will be speaking about is also a lot related to Luke's work, because Luke has done the GC and of course other parts. So about the protect bugs first. Well, if you look at a page for a package like this one, it's a CRAN page with results, check results for the package. So we regularly run, CRAN team regularly runs checks for each packages, and well, you can click on that, right? And then you see below, at the very bottom, there are these additional issues, and the rchk additional issues are results of my tool that is checking for these protect errors. I will say what they are later. And so if you click on that, on this package, you will see a report, and part of the report is that there is an unprotected variable somewhere, and it tells you the file name and the line number where the likely error is. Actually, this example is a real example from a package that has a bug, right? So I will get to this package later. And so now some introduction, like what are the protect errors? So when we program in R only, we don't have to worry, right? So this is the well-known example, convolution example in R, and you can see that first of all, we don't explicitly allocate memory. Okay, at line 4, we create a numeric vector, and the intuition is that the allocation happens somewhere there, some memory to back the vector, but it may not happen there, it may happen later, it's not specified. But yeah, something allocates there. But we definitely don't have control when the things get deallocated. This is done by the garbage collector indeed. And specifically, the garbage collector can find out when we don't longer use objects from local variables. So for instance, there is this local variable j that we use from line 7 in the for loop, and this variable goes out of scope at line 10. And after line 10, the garbage collector knows that we are no longer able from R to use the memory for I, and so it can reuse it. So when there is need for more memory, the garbage collector can reuse it, and we don't have to tell it when, and we don't have to tell it and can't tell it which local variables are pointing to some objects. In C it's different. Like when we program in C for R, well, we have to tell the garbage collector because the C runtime is not able to provide this information. So there is an API for that. It uses this pointer protection stack or the precious list of pointers that have to be kept alive by the GC. And in the talk, I will just use the most common one, so two functions to use the pointer protection stack, protect and unprotect. So protect x means that x is a local variable that points to some object, and we are telling the GC to keep that object alive because we are using it. And unprotect, with unprotect 1, for instance, says that we don't want anymore the x that we have protected last. So it is a stack, and we say how many things from top of the stack we no longer need. So that looks easy. This is an example from writing R extensions. This is a correct example. It's the only correct code you would see in this presentation. Yeah. Okay. So yes, from the manual, and you can see that at line 5, we allocate a vector and protect it. And it's like I would say that we protect A, but in fact we are protecting something in memory, and A points to it, right? At line 6, we allocate another vector, and this means that a garbage collector may run at this point, but it cannot reuse the memory used by A because it's protected, right? So it's okay. And again, we allocate at line 8, but it will not kill the memory used by A and B because they are protected. At line 14, well, we unprotect these three variables we put on the protection stack, and that's fine. So this code is okay. Okay, so this is the code from the package I have shown at the beginning, the report for. So this is a real bug, and someone simply forgot to protect. So at line 1, we allocate a vector. At line 2, we allocate another vector, but we have not protected the one at line 1. So garbage collector may run and may reuse the memory for image, and then later the code accesses image, and if you run it, it may crash, right? So this could happen. I have run the test and it's segfaulted. It's very, very hard to find out why, normally. Often I debug packages most of the time, actually. As I work on R, I have to test my changes on packages, and then I spend sometimes days, sometimes weeks debugging, and often I find out that I have only woken up a bug that has been there before. Of course, sometimes it's my bug, of course, but sometimes it's someone else's bug that has been there before but did not show up. And very often these are protect bugs, and this is also why I wrote a tool, and Luke wrote another tool, and we have some tools to catch these bugs, right? Yeah. So it can segfault. So this is a more complicated example, or slightly more. In this example, we can see that the author already used protect and unprotect. That's a good step, but not quite well, right? So if you look at line 5, so we are allocating a vector at line 5, right? So garbage collector may run, but what about F, right? So F has been protected at line 1, but unprotected at line 4, right? So that's a bug. I don't know how this could have happened, but like F at that point is unprotected, it can be reused, and you can see that at line 8, F is used, but it can be already the broken version of F at that point. The same bug is repeated in this example down below. You can see that when we allocate at line 12, ans is unprotected at that time. But we are returning ans, that's the answer, the result of some function, but it may be corrupted already at that time. So again, it's a real error. Okay. So one more, well actually there will be 3 more, but yeah. This one, so yeah, this may be getting harder. Well, so the problem is at line 5. So at line 5, well, we are allocating, so we are allocating and protecting M, that's okay, but how, right? So we call duplicate M, which creates a copy of M and returns a newly allocated object. And then we pass this newly allocated object to as integer. Well, and what is as integer? If you look into the source code, we see that it's a call to coerce vector, very common function. And how coerce vector works in this case? Well, it calls coerce to integer inside R, and what coerce to integer does? Well, it allocates space for the result at line 10 and protects it. And later on it uses its input, of course, because it's converting. But at this line 10, when it allocates, garbage collector may run, and it will may destroy the input of the function, which has been the result of the duplicate call, right? So actually what is coerce to integer doing is right. That's a convention in R, in this API, that this is the caller who is responsible for protecting. So the bug is at line 5, and it is that we must protect the result of duplicate before passing it to as integer. And then we can unprotect later, of course, but yeah. So this is another real bug. Unfortunately, I must say that it was very easy from the list of the bugs reported to find real bugs. The tool can make an error. The tool is sometimes confused and says something is a bug when it isn't. But it was unfortunately too easy to find the real ones. So there are still a number of bugs in packages. So, okay, this is another example. It is not the same as before because there are some exceptions. I said that you have to protect before calling a function. But there are some exceptions. Sometimes you don't have to. And one of these exceptions is setAttrib function, which is, of course, used very widely. You are adding an attribute to an object. And by adding something to an object, that something will be protected through that object. So if res is protected, after this call finishes, this mk string, the result of this mk string will also be protected. So to make it easier, the function setAttrib will protect its arguments at the beginning. Yeah, that's nice, but this is still wrong. And this is extremely common error in packages everywhere. So what's the problem? Well, we are passing two arguments, and both of the arguments are calls to a function that allocate. MK string is returning this newly allocated object. Well, install is more complicated. It's not important. It would be a bug even if it wasn't. But install may allocate as well. It creates a symbol, puts it into the symbol table. If it's already there, well, it just takes it from the symbol table. The garbage collector knows about the symbol table. So the result of install class will always be implicitly protected. But the function may allocate. And now, the arguments of a C call may get evaluated in any order. The compiler is allowed, C compiler, to do it in any order. It's important for optimizations. Actually, in R, we have the same thing. We have documentation, specification, and some behavior is specified and some is unspecified. And we can change the unspecified behavior to make R faster or something. Unfortunately, people are relying on the unspecified behavior, and then by changing it, we break things. Yeah, okay. But in this case, the unspecified behavior is on purpose. It's a good thing, and it's in C. And, but a common order is that MK string gets called first. Also, it's on my machine. And this is the one that causes the bug. So MK string gets called first, allocates an object, returns this object, and then install gets called. Well, it may allocate a new object, may run a GC, and the GC may destroy the result of the MK string. So this will happen even before setAttrib can do anything and can protect its arguments, right? So it's another bug, extremely common, and this one would be almost impossible to find because it would trigger really rarely. Because the symbol, especially class, would be very likely already in the symbol table. So usually it will not crash, but if it crashes, of course, it's bad because you have no chance finding it. Okay. And the last example, this is also a common bug. So line 1 allocates and protects mean. Line 3 allocates and protects verbose. And then we check something. And at line 7, if something is wrong, we just return from the function. Like line n and more would we just continue with some computation, but 7 is some kind of error. And we return without unprotecting the values. So we leave the 2 pointers on the protection stack after executing the function, which is a bug again. What can happen this time? Well, if we call this function repeatedly, we can run out of the pointer protection stack, run out of memory, our crash. Probably with an error message in this case, so it will not be as bad as it could be otherwise. Yeah. Also, you can get a runtime error in this case, but unfortunately not always. Okay, so how to prevent these bugs? Well, there are some rules that are good to follow, like defensive programming rules, when writing code to prevent the errors from happening. I have written them down somewhere. This is just a simple summary. I said already some of that, right? So caller protection, this is used everywhere in R. Arguments of functions have to be protected by the caller. The callee can depend on that the arguments are protected. We should defensively assume that all functions allocate. Right? Some functions, in fact, do not, but it's really, really dangerous to depend on that because that can change. That depends on all the callees of that function, right? This can be some internal function somewhere in some package you don't own, you don't control, or in R itself. And sometimes we have to, of course, we are scared, particularly because we know this, but sometimes we have to introduce allocation into function that didn't allocate before, and it impacts everyone who is using that function, right? So when writing code, one should defensively assume that any function may allocate and therefore run GC. Yeah, pointer protection. Oh yeah, a similar thing. When a function is returning an object, we should defensively assume it may be an unprotected object. Not always it is the case, but almost always it is. And again, this could change. Pointer protection balance that I said already. Functions should unprotect everything they have protected, so that the pointer protection stack works like the normal call stack for C functions. Yeah, okay. And so how to detect the bugs? So there is the tool I spoke about that I did that does static analysis. I spoke about that already. The downside is that it has false positives. Sometimes it's wrong. Sometimes it tells you there is a bug, and this line it isn't. But in my experience, I often get emails from people, of course, who ask questions, is it a real bug or not? Should I fix it? Or they even complain, oh, this is not a bug, and I'm asked by CRAN to fix it, right? Often, almost always, when the tool is confused, it is because the code is complicated, and even it's hard for a person to understand the code. So it's good to fix it, even if it's not a bug, right? Of course, in some cases, it's also a limitation of the tool, but yeah, often it is that it's better to fix the code to make the tool happy, even when after 1 hour of proving on the paper you can prove that it is not a bug. It's often the case, like when I spend few hours trying to justify it's a bug, and then I can prove to myself, oh really it is not a bug, because by looking by 10 other functions that are calling, I know that in this context really some type is not a list but a vector, and if it's a vector and you get the names attributes, yes, it will not be allocated, right? But if it's too complicated, it has to be corrected. And then the limitation of the tool is that it doesn't understand C++ code and doesn't understand some very complicated code. And for that case, we have a runtime tool that was done by Luke earlier. And the tool gctorture, it works by provoking the garbage collector more often than it runs normally. So it's more likely to crash the program, and then you can just find out by testing. The downside is that this is very slow. So either you have to play with parameters, like how often to run the GC, how long to wait, or on long programs, yeah, it will not work. On the other hand, it can find bugs you can't find normally. And to make this more efficient, it's good to compile R with barrier checking, which means that on many operations with pointers, the pointers are checked whether they are corrupted in some simple way. So if you compile R from scratch, but it's the normal standard R, with the strict barrier checking, and you use gctorture, which is documented, it will find some of these errors as well. Okay, so that was about protect bugs. I'm happy to take questions now and offline, and if you have questions whether some report is wrong, you can ask.